For this lab, our experimental goal was to learn how the Gauss gun setup impacts the force of the ball bearing that's being shot off. Our research question was, what is the relationship between the number of balls in the Gauss gun and the force of the released ball? Our main finding was that the best relationship was a third-order polynomial, and for that graph we had an R-square valued of 0.39. The trial that had 3 balls attached to the Gauss gun had the highest force. Our main model for our experiment is in the lower right-hand corner, with the A ball being rolled towards the magnet, which is the square, and the last ball on the end, in this scenario, the 3 ball being released and the transfer of energy in the direction of the arrow. The energy pie chart in the top right corner is what we were expecting to happen. We were expecting an elastic collision, but this did not happen. We ended up with an inelastic collision, which meant the kinetic energy was lost to vibrations, which increased the internal energy instead. On the left, we have a system schema, including the magnets, the earth or the ground, ball A, which is being pushed into the magnets, and ball 3, which is the ball that's being released.
For our experimental design, we constructed a Gauss gun using a magnet placed within a plastic tube leading up to an IOLab force sensor. Anywhere from 2 to 5 metal ball bearings were connected to the magnet and aimed toward the force sensor. A separate ball bearing was then placed 2 centimeters away from the magnet on the other side and released. Using the data collected from the IOLab, force versus ball number graphs were constructed in Excel, and the relationship between the two was measured with an R-squared value.
After collecting data from each of the 6 trials using our Gauss gun, we then graph the results using Excel. On our x-axis is the number of balls, and the force measured using the IOLab is on the y-axis. The first graph shows all the data points we used, while the second graph shows just the averages from each of the number of balls. With the first graph, we had an R-squared value of 0.39. This was still the strongest correlation that we saw comparing linear relationships, first-order polynomial, second-order polynomial, and third-order polynomial. And then we can see this relationship is further explained when we compare just the averages, and there's an R-square value of 1. After seeing these unexpected results, we decided to speak with Dr. Henko and see what possible sources of the decrease in force could be. After speaking with her, we thought about the collisions becoming less elastic as we add more balls. As you're adding more of the ball bearings, they're less tightly bound by the magnet, especially because we were using a pretty weak magnet, which means some of the kinetic energy is being transferred to vibrational energy between the balls, and they're moving within each other instead of using all of their force to move the final ball. This means it's a non-elastic collision, and then the kinetic energy is being transferred to internal energy instead, and therefore we see less force because the final ball is moving much more slowly than we were anticipating.
In conclusion, the relationship was best modeled by a third-order polynomial, possibly due to the weak magnet allowing vibrational energy to transfer between the balls. This is most likely because as the soon-to-be-released ball bearing gets farther away from the magnet's hold on the ball is weaker, so the amount of potential energy that can become kinetic energy is also lower. Improvements that we could make on our current model are tightening the force plate after each trial and open-top tubing. For future work, we could try different numbers of ball bearings or alter the number of magnets.